Well, good morning, evening, and whatever. Welcome. We will get started so that we run on time, and I'm sure people will join while I'm doing my waffle. This is a side meeting at IETF 112. Its purpose is to bring some discussion of new work specifically related to routing and bring in some speakers who are not usually around the IETF, and to have a bit of a discussion about routing and routing research. Because this is part of the IETF, note well. We are covered by the IETF's patent and IPR and copyright policies, and by participating in this meeting, you agree to those policies. If you're worried about that, go and read, and if in doubt, don't participate. Note to you all, this meeting is being recorded, so if you've got any concerns at all about your participation being recorded, then obviously take that under advisement. This will be a 90-minute meeting. It's on WebEx, so please keep yourself on mute as you participate until it's your turn to speak. If you want to interact, you can raise your hand in WebEx and I will see that. And you can type away in the chat window where the speakers will be able to respond to you when they're not busy speaking. There may be a little time after each speaker for questions and discussion, but we've also got a dedicated slot on the agenda at the end for an open discussion. And you're welcome to follow up on our mailing list if you like. We're also live streaming on YouTube, and I know there's 10 or so people watching there. There's an Etherpad if you want to go and record comments, and we'll try to keep that up to date as minutes. And the materials, the slides for the meeting are already posted. And once we've got the recording sorted out, we'll also put it there on our GitHub. So the context of all this is that the organisers, who are Dan and myself, are looking at research into what we call semantic routing. So this is routing on additional semantics carried in the packet. And we're also looking at the wider and we think neglected concerns that accompany routing research. So what we hope to get out of this meeting ourselves is some more general points that we can take away and apply to this. So there are a number of internet drafts related to semantic routing, which you're welcome to go and look at and discuss as you see fit. The concerns that I mentioned around routing research, well, we want to understand what the key drivers are for new routing solutions. So why people are researching them, what they're pushing for. And we want to get a better understanding of the benefit and drawbacks of doing this type of work inside limited domains. And then we're pretty worried about how, when these new proposals come along, they don't properly look at the impact on the existing routing infrastructure, and the research is not necessarily independently verifiable or repeatable. So we want to look at that. And then we also, as a sort of side issue, want to understand where this research can be discussed. So today's agenda. Firstly, an apology to anyone who's come along hoping to hear Vasilios Giatsas talk. He's had an emergency and had to drop out, but huge thanks to Gregor Hayward, who has stepped into the breach very valiantly and extremely the last minute. So he will come along and talk about end-to-end privacy for identity and location with IP, which is actually quite an interesting paper he's got there. So I hope that fills the gap. Then Michael Kroll will talk about remote method invocation in ICN. And our third speaker is Jeff Houston, who I'm sure many of you know, and he's going to ponder on centralization of service provisioning and its impact on routing. And then we'll have our open discussion, and I'll wrap up just in the last couple of minutes to talk about a little bit about how we might bring our research work to the IRTF. As I said, to discuss, raise your hand in WebEx, and these are some questions that I'll bring back in the open discussion session. So I'll stop sharing and allow Gregor to share his slides, especially if I can persuade WebEx to stop sharing. There we go. So Gregor, you can share away and I will go quiet.
Thank you, Adrian. Is that displaying correctly now?
Yeah, that looks good.
Excellent. Okay. Hello, I'm Gregor. I'm a PhD student at the University of St Andrews. I'm presenting on end-to-end privacy for identity and location with IP. This talk is based on a paper we presented at NIPA. So if you saw that, then you'll be in a good place to come up with difficult questions for me at the end. This is work that was done with my supervisor, Salim, and fellow PhD student, Rio. This talk is replacing the ties that unbind. However, there are parallels in between this work and that work. We're both trying to break some of the bindings between host names and services and IP addresses, but we have slightly different reasons for that. The work that we've done is to try and improve IP layer privacy. So the problem is that the reuse of IP addresses between different layers makes it hard to protect privacy. The network stack is good for reducing complexity and essential for making networking function. But when there are problems that aren't clearly encapsulated, they can be hard to find and they can be hard to fix. So an example of this is the reuse of IPv6 addresses. At the transport layer, there are endpoint IDs. At the network layer, they give routing information, and then at the link layer, they can include hardware information. And because they're being reused for different things at different layers, values that aren't necessarily sensitive in one place become sensitive as a kind of emergent behavior. In our work, we wanted to stop an on-path attacker from exploiting visible header information to compromise privacy. And we wanted to do this without putting trust in a third party. The way that we've decoupled IP address semantics is by separating node identity and network location. So this is similar to what IPv6 already does, but we want to take it even further. So the location information is what's encoded in the routing prefix, the upper 64 bits of the IPv6 address. It's a value that's used globally to uniquely label a subnet, and it has to be in order to make routing work. And so it has to be managed globally and allocated through an ISP. Identity, on the other hand, is encoded in the interface ID, which is the lower half of the address. Although it's still used globally in the address, it can be managed or generated locally through something like Slack or DHCP, and it uniquely labels an endpoint. Making a distinction between these values is useful for the privacy work we're doing, but it has other uses as well. So the Identifier Locator Network Protocol, ILNP, uses this explicit separation of identity and location to facilitate mobility and multi-homing. And it does this by making changes only to the end systems and not to any of the core network infrastructure. The diagrams show how IPv6 addresses and the ILNP equivalent and identifier locator vector compare. They have the same syntax, but we label values differently and use them slightly differently. Our privacy solution builds on ILNP. And so I'm going to skip over a lot of the detail of how ILNP itself actually works and just focus on the bits that we can use. So I'll highlight the differences where they're relevant, but this is not an ILNP tutorial. The first thing that we want to do is improve identity privacy. So ILNP replaces the IID with a node identifier, or NID. This is a value that labels a node rather than an interface. So in a multi-home system, you'd have one NID rather than having multiple different IIDs. They have the same semantics, and so it could be generated and used in more or less the same way. And there's a variation of SLAAC that just uses a randomly generated value. So we can use that to create NIDs that don't reveal any sensitive information. We can also have multiple NIDs in use at the same time. So we could have several different transport layer sessions, each using different NIDs. And if we generate new ones for every transport session and then expire them as soon as they're done, we can make these values ephemeral. So this means that the value that gets exposed to the rest of the network is random and temporary. So it can't be used to correlate future activity. The diagram on the left here shows an attacker's view of a regular ILNP or IPv6 connection. The attacker can see everything that Alice sends to Bob and can correlate consecutive transport sessions. On the right, Alice is using multiple ephemeral NIDs, and so appears to the attacker to be several different nodes. And if she were communicating with multiple different endpoints across the internet, then that would become even harder to track. This is a similar concept to temporary address extensions for SLAAC. Both change the NID or IID over time. The advantage of ephemeral NIDs is that you can use multiple ones simultaneously rather than having one IID for all sessions in a particular window of time. And you can manage them at the transport layer, which simplifies some of the work expiring temporary addresses. Because these are just replacing the interface IDs in IPv6, this does not have any implications for routing. That is all tied up in the routing prefix. If we are using ephemeral NIDs, then we can kind of treat the lower 64 bits as safe. An attacker can't exploit those, and we can look to the rest. So this is the routing prefix in IPv6 or the locator or L64 in ILNP. Unlike in IPv6, ILNP excludes this part from the transport state. So one transport session could have multiple different L64s, and then each NID L64 pair on a node would function like a different usable address. The challenge that we face when trying to protect location information is that we're competing with routing concerns. So from a privacy point of view, we might want to hide all the information that we can. But from a routing point of view, we need to have it visible so that we can send traffic to the right place. One solution to this is to spread traffic across multiple different paths by using multi-homing. So the information is still all exposed in the packet headers, but it's harder for an attacker to find because they need to be present on all paths to see all packets. And ILNP makes multi-homing really easy. Again, the figure on the left is a regular ILMP or IPv6 connection. On the right, Alice is using multiple paths, so has 3 different L64s, and uses those to send traffic out along 3 different paths, and the attacker, to get the same view that they had before, has to be present on all of them. This might have limited value in certain cases. Even if the attacker is just present on one path, they can still see one L64 from one packet and get some location information from that. But it is less likely that they can see the entire flow. And so some kind of untargeted surveillance by mass traffic analysis will give an incomplete picture. If we do want to take this further, we can try and avoid exposing our real location at all. So the known solutions for this are things like VPNs or Tor, where we set up an encrypted tunnel and make all our communications appear to come from somewhere else. This is not without costs. So with a VPN, there's a single point of failure. You have to trust that your VPN is both honest and is completely secure and is never compromised. Tor's trust model is different, so it avoids that problem, but has a more significant performance cost. The ILMP solution takes advantage of L64s being excluded from transport state. This means they're also excluded from checksums, and so we can change them on the fly. A router can rewrite an L64 for any packet that it forwards. We call a node that does this a locator rewriting relay, or LRR. They have a similar function to, or they can function in a similar way to a VPN or Tor relay, where traffic goes in with one source locator and comes out with a different one. The advantages of this are that we don't have to do any cryptography, so we don't have any processing overheads from tunneling. And this lower performance cost means that a Tor-like relay chain is less prohibitively expensive. And so we can use that to sidestep the single point of failure in a VPN-like model. We can also do this at the network layer. Unlike Tor, which has an application layer tunnel, this would work for anything that used an ILMP network stack. And we've got existing work to show that you can use normal IPv6 binaries over a modified network stack to get all the benefits this brings. The disadvantages are that this is going to be weak to the same kind of attacks that work against Tor. So an attacker can try and correlate the before and after traffic based on packet and session timings. And because we're not using cryptography, it's actually going to be even easier. They can use the payloads rather than just the metadata. And so the processing costs are going to be lower. This kind of attack will work against any low latency system. Tor acknowledges it and doesn't claim to protect against it. The difference here is how much offline processing is needed. And because that can be done offline, there's kind of diminishing value in making it harder. Ultimately, there is a trade-off here. Tor will be less vulnerable, but we have the potential for better performance and a more universal solution. The exact method used will depend on what our users' priorities are. The figures on this slide show the setup for Tor and for the LRR equivalent. They have a very similar architecture, and even down to the attacks. The only difference is that the layers of encryption are missing. To get this to work, we would need some kind of control protocol, which we've not yet written. But once we have that, setting this up will be relatively simple because the chain of LRRs would function like a virtual circuit and wouldn't need any endpoint support. To show that this actually works, we've tested it in an emulation of ILMP in an IPv6 lab. So the figure on the left shows how we emulated ILMP. We used IPv6 multicast as our pretend physical layer, and then using each multicast group as a shared medium subnet, which would then have its own locator. Our routers would then function by forwarding packets between multicast groups. And this let us emulate whatever topology we wanted to test. We used UDP as our pretend link layer and could treat each datagram as if it were a frame. And then ILMP was encapsulated within the UDP datagram. The figure on the right shows an example topology. So each oval is one of these multicast groups. We have a couple of routers that are present on a local subnet and a kind of pretend backbone network. And this means our two nodes can test out different defenses while communicating over this setup. Using this, we can get some results. So we did a series of experiments. In each one, Alice would send the same set of communications to the same set of remote nodes. And the tables here show the different views attackers would have for different defenses. So on the left, we have the normal connection. Alice has a single NID and L64. So the attacker will see one address and can correlate all traffic back to her, regardless of where it's going or when it happens. In the center, Alice is using multiple ephemeral NIDs, so N1, N2, and N3. The attacker will see what looks like 3 different nodes on one subnet as being the sources of these communications, even if they're happening simultaneously. And then on the right, Alice is using ephemeral NIDs and multi-homing. So she has 3 apparent NIDs and 3 L64s. So that creates the 9 visible addresses. And even if an attacker is trying to match them up, it will look like 3 different nodes on 3 different subnets, and they'll need to be present on every path to get that full picture, which means their job is much harder. So as a summary, ILMP has value as a way of improving privacy by separating identity and location information. We can protect the independence of each flow by using ephemeral NIDs. We can use multipathing to make traffic analysis harder, and we can use LRRs to provide a low-cost way to bring stronger privacy protection to all applications. Thank you very much. I think we've now got time for some questions, unless everyone wants to keep those for the end.
Yeah, we've got a couple of minutes, and I see Andrew Alston in the queue with his hand up. So go ahead, Andrew.
Yeah. So firstly, thanks very much. Interesting presentation. Now, firstly, let me say that I'm a big fan of privacy, so I can't even believe I'm actually going to be asking this question, but I have to ask it based on countries that we found ourselves operating in. How do you deal with stuff like lawful intercept on here, etc., when I'm handed a court order? Because I have to ask the question, because if I were to turn this on in certain jurisdictions, well, it could get me thrown out of a country, it could get staff arrested, etc. And so if I've got a way with lawful intercept, etc., to deal with that, where I can still have some tieback under a court order, it would help. Not that I like having that situation at all, but it is a reality that I have to deal with in certain places. So I'd just like to hear your thoughts on this.
Yes. So a lot of this is functioning kind of like a VPN. And so without knowing the specifics of all international law.
Yeah, you see, that alone, there are certain countries where VPNs have been declared illegal, believe it or not.
Yes. So if it's against the law, then it's against the law, and there's only so much the technology can do. There is some potential. So one of the ideas we've looked at is setting up and having your ISP run an LRR. So it would function kind of like carrier-grade NAT, where everybody behind the NAT would appear to be on one locator, but the ISP would still be able to log that mapping. And if they had a court order, they could then consult their logs and work it out backwards.
Okay, thanks. That helps. Like I said, sorry for asking the question, and it's not a question I like to ask because I like my privacy. But well, you know how it goes.
Yeah, it's the world we live in.
Yeah.
Okay, thanks, Gregor. Stay around for the chat at the discussion at the end, and have a look in the chat window and interact there with Dino, who's comparing and contrasting with Lisp. Okay, so next up is Mikael. If you're there and you can share.
Hi. Hopefully you can see me and hear me. Let me share my screen.
I see and hear, and
The Firefox prevents me from sharing my screen. Let me try an application.
if you need it, I can share, and you can tell me when to change sides.
Yeah, I'm afraid we'll have to. Let me
No problem.
Actually, does it work now?
You did it. Yep, that's fine. That's good.
Amazing. So, hi again. My name is Michał Król. I'm a lecturer at City University of London. I'll talk about remote method invocation in ICN. So I guess that the majority of you know about ICN, but just to make sure that we're on the same page, I'll give a brief introduction. So ICN is information-centric networks. On this figure, you see IP for contrast, let's say. So in IP, we have IP packets. Every single packet has a source and source and destination IP address. We use the destination IP address plus the routing table to forward the packets. Once the recipient receives the packet, it uses the source IP address to respond to the specific packet. Now, in ICN, this is slightly different. Well, first of all, in IP, we send a packet to a specific location. In ICN, we don't care about the location. We just want the specific content. So in ICN, we have two different types of packets. We have an interest packet we can see as a request packet saying, hey, I want this data. And then we have data packets, which are replies for a specific interest. So basically the data itself. In the interest packets, we have only data name that we are requesting. In the data packet, we have the data name that has to match the name in the interest packet, the content itself, and then the signature. The important thing is that the signature is issued by the producer or the creator of the content rather than someone who sends us the data. So this is in contrast to, for instance, TLS, where in TLS, the integrity is guaranteed by someone who sends us the data rather than someone who created the picture, video, and so on, whatever we are receiving. So if I want to download something from in ICN, let's say a video from currently happening COP26, I'll send an interest with a specific name. So here /VPC/video COP26. This interest will be forwarded using a routing table, which is kind of similar to IP, but instead of IP addresses and networks, we have name prefixes and the next hop as usual. On top of that, on every single router, we should have a content store. This is kind of like a cache. It's just that in ICN, every single piece of content will have a unique name, which makes cache management much easier. So when I receive an interest, first of all, I'll look at my cache. Hey, do I have this piece of content? If I do, I can send the response right away without bothering the initial producer of the content. In this case, we have only COP24 and 25. We don't have 26, so we have to forward the packet to BBC in this case. Now, you might have noticed at the beginning that in the interest, we have only the name of the content we want, so what we want, but we don't have a field that indicates who wants this content. So to be able to deliver the data back to the requester, we on every single router, we have something called pending interest table, which basically tells us if there is a data coming back with this name forwarded to this specific interface, which basically creates a reverse path towards the requester of the specific content. And the good thing about it is that if now someone else is requesting the very same content and receive an interest, we don't have to send it again to the producer, so in this case BBC, but we can just update our pending interest table. So when the data comes back, it also goes to another interface. So in this case, our interest goes back to BBC. BBC sends back the data. So once we receive the data, we'll clean up the pending interest table and we'll send it to the initial requesters. So once we also receive the data, what we can do, we can first of all add the specific content to our content store. So when we have another request for that, we can just give it directly from the cache. We can also, if you want, maybe update the routing table. So now if there is someone else looking for the very same content, we don't have to go to the BBC, but we can give it, we can forward the interest to someone who already downloaded the video. This can make a big difference if those two nodes are in the same local network, while BBC is far away in the cloud. So by default, ICN is efficient in retrieving static data, but we're looking mostly on how to use this system in network computing. And there is some potential because, well, in ICN, we don't care about the specific location, but we are say, hey, I want this data. So maybe we can use this kind of semantic to say, hey, I just want this to be computed regardless of who actually does it. We also have explicit names in the interest data, which are exposed to the network layer, which might help in implementing maybe some more sophisticated load balancing. And because of caching and naming every single piece of data, it makes it also very easy to reuse some partial results. So if I ask the network to compute something, and then there is someone else requesting the same thing, we don't have to recompute it again. We can just give the results right away. So the problem is that ICN was designed for the static data retrieval, which makes it sometimes tricky to implement in network computing on top of that. So let's imagine that we have our client here. We send an interest saying, hey, can someone execute this function for me? It will be forwarded to the most suitable node in the network. Hopefully, this server will produce the result and send it back as a data packet. Remember, in ICN, we have this pending interest table, which allows us to send back the results of the data back to the original client. So if the data comes back, this is easy. The data will clean this interest, this entry in the pending interest table. However, when the data is not coming back, we still have to do something with it. This usually means that the interest or the data was lost. So we would like to clean it after some expiry time. And when we want to use it only with static data, this is easy because this expiry timer, we can base it on the RTT. So let's say if the data is not coming back after 5 seconds, we know that the packet was lost and we just clean it. However, when we now want to accommodate some more sophisticated computations, well, now computing something and then sending back the results can take longer time, maybe even minutes if we do some image processing or some more sophisticated computations. So we have this mismatch between the network timescale and the application timescale, which can be the network timescale is based on the RTT, while the application timescale is based on the time that is needed to produce the data. Now, if we would use the network timescale, it means that we remove this entry after, let's say, a couple of seconds. If the server takes longer to produce the result, it cannot send back the result. The client can obviously resend the interest, but in ICN, we are not guaranteed that it will actually reach the same server. It can go to a different one, which means that we now instantiated another instance of the same computations and we cannot get the results back. On the other hand, if we use the application timescale and say, okay, let's make it expire after 5 minutes, if the interest or the data is actually lost, the user will have to wait until this 5 or 10 minutes expire to resend the packet, which makes it very inefficient. So we have the first problem that's actually difficult to support non-trivial computations in ICN. On top of that, when I send an interest triggering some computations, in the interest, we don't have any information about who sent this interest, because there is no sender identifier in the interest, which makes it difficult because, well, the server now doesn't know if this is someone who is authorized or not. And again, this is okay for static data retrieval because we can, well, just give the data to everyone. If we need some confidentiality, we just encrypt it and give the ciphertext to everyone. Only the authorized user will be able to decrypt it. However, here, if you are triggering some computations, we don't want anyone just to be able to use our resources. So problem 2 is that it's actually tricky to make the user authentication and authorization right in this case. And finally, if I want to do some image processing, I can again send an interest saying, hey, can you process this image for me? But in ICN, we have this one-way information flow. So when I request something from the server, the data is mostly flowing from the server to me rather than in the other direction, which makes it difficult when we want to do something like image processing. So we have to submit a large payload to the server. So to solve that, we designed a naming scheme for this computations in network computation based on ICN. So first of all, we distinguish between referentially transparent and opaque functions. Referentially transparent, you can think about them as deterministic. So basically, if I invoke the same function with the same input parameters, I'm guaranteed to get the same results. So for those functions, we create a name by taking the function name and then the hash of the input parameters. So we are sure that if someone calls the same function with the same input parameters, it will end up with the very same name. So we can take advantage of the caching of the results and also merging of those entries in the pending interest table. On the other hand, for the referentially opaque functions, those are the function non-deterministic. So even if I call them with the same parameters, they can give me different results. So we do not want to have result sharing in this case. So for the names, we take the function name again, but then we append something unique or random at the end so that we disable caching and merging of those entries in the pending interest table. And then we also introduce the func names. So by default in ICN, you have those names specifying the data, but the func names specify a specific instance of a function running on a specific node. So the name is constructed by taking the identifier of a node, then the function, and then the state if the function is shared between multiple clients, let's say. Having this, we can hopefully solve the problems that I mentioned before. So now if I want to trigger some computation, I can send an interest with the function name as before. The server can now start producing the result, but it can now respond to me right away with the data, and the data will contain the func name. So this is this name specifying this node and specific instance of the function running on this node. And then information, let's say, I should be ready with your results after 5 minutes. Now the client can wait for the specified amount of time and then can send another interest, but now using this func name, which now we guarantee that this interest will go to the very same node that is now producing our results, and the node can now return the data. So we solved this problem 1, where there was this mismatch between network and application timescales. We also introduced a 4-way handshake. So again, if I want to introduce some trigger some computation, I set an interest with a function name. Now this interest will establish a path between the client and the server, allowing the server now to send an interest towards the client. And client now can respond to this interest with some data, providing some input. And obviously then the server can respond to this first interest with the second data. So basically here we implement the full duplex communication between the server and the clients, which first of all enables client to submit some data to the server, and then also to perform authentication, authorization, Diffie-Hellman if you want some confidentiality and so on. So at this point, you won't be wondering why do we bother with all those handshakes and names and when we can probably do it also easier in IP. And this is the case, but when we get it right, we can also use ICN to significantly simplify the application layer of distributed programs. So to showcase that, we considered a use case where we implement an airport healthcare screening. So we would like to detect people with pulmonary diseases based on the audio samples. So you can imagine some sensors being deployed at the airport. They record some audio. We want to detect cough sounds, and then based on analyzing these cough sounds, we can distinguish between dangerous and non-dangerous cough. If this is the dangerous cough, we can just raise an alarm. And if you'd like to deploy it using some commodity devices, so not like a very expensive central node, we would like to take advantage of distributed computing. So just send some requests for processing of those audio samples to the network so that we collaboratively produce the results. Now, if you would like to do it if you would like to write a sequential code for this, here we have like a very simplified pseudocode in Python. So we have a while loop. We will record some audio samples, then we will remove some speech from those samples for privacy preservation. We can then extract some features, and at the end we can add an annotated sample to our class so that we are able to analyze multiple samples at the same time. Now, if you want to create a distributed application out of that in IP, this will actually require quite a lot of code to handle the networking, to instantiate some function and so on. But with using the system that I described before, we can actually do it very quickly. So we introduced a framework that only requires to usage of some decorators. So we introduced 3 decorators just to distinguish between referential, transparent, and opaque functions, and then CFN actor, which basically defines a class. And then we have a very single method, cfn.get, that I'll show in a second. So if you want to turn this sequential code into the distributed application, we just need to annotate every single function. Once you get the parameters in a function, you just call cfn.get on top of that, and that's it. And with this, we can have actually a whole ecosystem of nodes or a whole network running this application collaboratively, meaning that the node will instantiate the required function when needed, will send the required interest and data back. We will wait for the results, we'll block when needed and not block when not needed, and so on. And again, this is easy to do just by simple annotation of the code. On top of that, we also build a system called named function as a service. So this is a function execution environment. And the vision here is, again, we have a network and we'll bombard it with some requests saying, hey, compute this for me from various different applications. And we want the network to kind of figure out how to compute all those requests in the most efficient ways. This system is based on the unikernels. Unikernels are kind of like Docker containers. Basically, we can just download it, and then we can instantiate it on top of a hypervisor on our bare metal. We can just feed some input parameters, and we'll get back some outputs. And again, in ICN, this is useful because every single unikernel or a function can be also named. So if I decide to run a function as a node, I can just request it from the network, and someone will just give it to me. And once I have it, I can just instantiate it and start running the computations. Now, I have a short video that I wanted to share as well, but I have to reshare my screen, I guess. Hopefully this works. So this is a simple illustration how it works. We have a network again with some nodes. Here we have one node running the functions. Now we can send request to get some results out of that. The request goes to the function, and this works. However, it's kind of suboptimal because, well, we have multiple hops to forward the request to the node. If it is something delay sensitive, say augmented reality, this can be a problem. But because we use ICN here, those nodes can see that actually there are a lot of requests for those specific functions. So if they have some spare capacity, they can just request the unikernels for this specific function and run it locally. And now the advantage is that, well, we get rid of this processing delay, so forwarding delay, and we can reduce the overall latency of getting the results. If one of the nodes gets now overloaded, it's not a big problem. another node will now start seeing requests for the same function, can download the unikernel and help with producing the results. And the good thing about it is that because those names are exposed to the network, we don't need any communication between the nodes. So the only thing we need is just to observe the traffic that is being translated, that is being forwarded. And yeah, I think that's it for me. Thank you.
So thank you very much for that. We have literally a minute if anyone wants to slip in a question now, or they can take it to the chat, where I see that Dirk has already typed a question. Maybe that's the best thing to do. So Mikael, if you could have a look at the chat and talk there, and then we can bring questions at the session at the end, and that gives us plenty of time for Jeff to enlighten us. So thanks, Mikael, and over to you, Jeff.
Pressing unmute, and I will start. I'll share my screen.
Brilliant. And we should say thank you, Jeff, for getting up at what is a ridiculous time in the morning.
Well, the rest of the IETF week has been even more insane. This thing wants me to show. No, let's try a window. Sorry, I'm just faffing around here with WebEx. I'm not a usual WebEx person. Can everyone see that title slide? Yes.
That's good for me.
Okay, so I'm going to launch the rocket ship and go to a very high altitude. And secondly, I'm going to go in precisely the opposite direction of the previous two speakers here. Because what I was asked to talk about was this more general view of what we're doing in the internet environment and its impact on routing, right? So what we're doing in the internet environment is centralizing like crazy, like that's obvious. But it has a pronounced impact on routing, and way beyond routing tokens or resource identifiers or identities, way beyond that. Now, I've got 20 minutes, right? But time is short, and these are really fundamental topics. So I'm going to move relatively quickly and just skate across details and try and keep this at a very high level to kind of look at where we are as an industry, why we've made deliberative choices in terms of the deployed internet, you know, folk making money, etc., and how those choices made by those players impact, you know, the entire environment we're working in. 2021 hasn't been unusual in many ways. You know, everyone shoots their foot. But when Facebook shot its foot, 3 billion users were affected, including, oddly enough, a whole bunch of people who had their businesses on WhatsApp. Fastly and Akamai shot various parts of their foot a little bit earlier in the year, and banks, actually airline booking systems too, but nobody noticed. All kinds of folk went down, and it was certainly a lot more than just Fastly itself. It was all the folk using Fastly, using Akamai. And we're going to see more of this because we're finding that while there's a rich world of service, underneath that is a very restricted and very small world of service provision. That's where centrality is happening. And what we're doing is actually concentrating. So, you know, as you remember a few years ago when we melted down the entire eastern seaboard of the US because someone found that baby webcams were running BusyBot, and BusyBot had a predictable root password, and you could inject code and it attacked Dyn. Dyn held a huge amount of DNS. The DNS died for the eastern coast of the US. But it's more than just a small number of people having a very critical role in the internet. It's actually the fact that we've produced monocultures. There's only one brand of banana you all buy, evidently, Cavendish. And if we go belly up on that because of viruses in bananas, I'm sorry, say goodbye to bananas. How many browsers do we have? Gee, Chrome and a couple of others. But the couple of others are so small in terms of market space that the world is Chrome. Take Google again and just look at that massively dominant position, because Google did invest. They invested in Speedy. They invested in what became HTTP3. They invested in Quick. They invested in BBR. In other words, it's dominant. And what's left, oddly enough, a bit like the long time ago when Sun Microsystems threw the network file system to the IETF saying, here, you look after it. What we're finding is Google's kind of throwing their products to the IETF going, look, you can develop this further if you want, but, you know, we've done all the work and we're going to use it anyway, so we don't care. And that's almost the best expression you have of what is massively market dominant. Look at the mobile device platform. Apple has still managed to maintain a small isolated space that it's put up the do not intrude walls against Google, and has globally around 12% market share. The other 88%, well, it's Android. Doesn't really matter who made the platform, it's Android. And, you know, if you've been following the chip world, a drought in Taiwan means that there's not enough totally clean water, and therefore the chip manufacturer, TSMC, is having trouble meeting demand. And all of a sudden, when you want to buy your car, which has, 300 different microprocessors, you better wait because drought in Taiwan. This is critical reliance. Now, we weren't meant to be here. We weren't meant to be here. The whole thing about this architecture was to take a massive leap away from the highly centralized and orchestrated telephone routing system. There was meant to be no critical orchestration components, no international numbered gateways. There's no Route Master 3000 doing Route Master things, controlling the internet's entire routing space. Nothing like it. There's no NameZar, and no ICANN isn't it either, controlling DNS resolution queries. And quite frankly, there's no internet service orchestrator. Like the previous two speakers have been talking about, this is all meant to be decentralized and adaptive. That damage was meant to be something that the system itself, without orchestration intervention, was simply meant to self-identify and self-detour. We don't have that. We don't have that. We've built something entirely different. What we've actually built on top of that platform of effectively decentralized adaptive systems and flexibility is actually an infrastructure that has a very limited diversity of supply. Very limited. There are points of astonishing critical vulnerability. Facebook's outage shows that level of astonishing criticality. Akamai has shown it too, Fastly. And, if Cloudflare ever has a whoopsie, and whoopsies are kind of inevitable in our world, you'll see again critical vulnerability. And we're doing a very, very increased reliance on these limited set of circuit orchestration elements. And so we're actually building centrality and criticality and vulnerability into our infrastructure. We didn't intend to, but we're doing that. Why? Some of you might remember Mike Odell, and I think he's still around somewhere. Hi, Mike. And what he said at the time, and I think this is about the year 2000 at an IETF meeting and elsewhere, is, look, the only real problem is scaling. Everything else comes from scaling. That's the only issue. And it's true. We spent most of the 2000s decade scaling the internet by a factor of 10 to the 12th. Everyone who had a clue, every piece of silicon, everything we could lay our hands on, every fiber cable was all about scaling, because effectively the job to be done was way, way larger than our capabilities at the start. And so we just scaled. And one of the things we tried to scale was routing. And I took this quote from Mike from 2000, because it's kind of true and no one really thought about it. The most complicated computation ever attempted by mankind, that's a big statement, is global routing. And the next one's even scarier, is if anyone had thought about it very hard before we started, they'd have been too scared to try. if you think about what BGP does in particular, but what the routing system does, near real-time, online, it's replicated, arbitrary topologies, built by lots of people who not only never met each other, but had completely different objectives. And it's a complex computation because it's piecewise constructive. Everyone does their own thing, and what you're after is a cohesive whole that pushes packets around. I think Mike is saying it's a miracle, and I think I agree with him. In the true sense of the word, it's a miracle. And so we have a huge reliance on routing. And how have we responded to routing and the pressures of scaling? Because the pressures are huge. So we needed to get bigger. And, you know, we took the old electro-optical amplifiers in fiber cables and turned them into optical amplifiers. We do all kinds of multiplexing tricks, phase amplitude, polarization. The digital analog converters that you know, detect signal coming out of the photons are now state-of-the-art pieces of brilliance. We get multiple hundreds of terabits per cable system now. And folk buy them and build them as individual entities. Look at the specs of Google's Echo cable that's just been announced for you know, an example. Everything is now server content aggregated. You'd be mad if you put a popular service on a single platform in a single location in the world and expected it to work. If it's popular, the definition is it's going to die. And you know, the rise of 4G, 5G, and whatever Gs you want basically means we're pushing gigabits all the way into the end system. It's bigger. It's billions of times bigger. Oddly enough, because we're pushing it to the edge, we got rid of latency. And if we get rid of latency, you increase the number of round trips per session, which oddly enough, together with capacity, increases the perception of speed. And quite frankly, all of these CDNs are doing is making the internet faster as a user perception. Because if I can bring the content to, you know, half a fiber mile behind my screen, then click to site is really, really fast, almost despite the DNS. You know, the packet miles to deliver content to users has shrunk like crazy. Most of the content people get in terms of just number of bytes is video streaming, 70% of all sold data, probably 80% these days. And that all comes over the shortest possible run. So this network is incredibly fast, and compared to 20 years ago when you were pushing packets across the servers on the other side of the globe, unbelievably fast. And not only that, but we're trying to cram more information in. Look at the DNS with its SVCB records. What we're trying to do is increase the semantic density of DNS transactions to actually reduce the number of transactions to make it faster. The whole thing about compressed handshakes in TLS and so on. It's all just cutting this out in terms of the extraneous detail. We're trying to build it better. Why? Because we're encrypting absolutely everywhere. And if you look at Oblivious DNS and Oblivious HTTP, which is actually a very simple approach to the more detailed ILMP efforts. And what you're trying to do is simply isolate knowledge. You're not trying to arm the network. All of this is at the application level. Why? Well, everyone, content, application, and platform, have all taken this privacy agenda up with astonishing enthusiasm. Networks are now not trustable. Now, it doesn't matter if they are or not, they're perceived as non-trustable. All common shared network infrastructure is untrustable. Sharing is untrustable. If you can't trust it, don't use it. So the next thing is a world of abundance. And this is, I think, almost the most critical thing, where all of a sudden, fiber's cheap, computing's cheap, and it's abundant. And when you have economies of scale, bigger is cheaper. And so a small number of enterprises have managed to capitalize through advertising a collective asset that you and I can't, my future purchasing profile. And the result of all of that is that a former luxury service, just only a few had access to, was transformed into this massive mass market commodity service available basically for free. I don't pay for search, but it's run by a very small clique of providers. So, you know, it's all good, right? Because all of these folk are doing what I want. They're desperately concerned about what I intend to do, what I intend to purchase, and they're intending to make that easier. It's all good. Yeah? Well, maybe. Where does this go? This is interesting because if you look at who's building submarine cable systems now, it's no longer telcos and it's no longer sharing. I'm building my own, says Google, says Facebook, says Microsoft, says Amazon. No sharing. Because transmission is so abundant that sharing's irrelevant. You build your own, because why share if you don't have to? Why do I use a network to bring consumers to service delivery points? If computing's so cheap and networking's so cheap, why don't I just replicate like crazy? The old internet was a just-in-time internet. I brought the user to the servers just in the time that they thought they wanted it. And it was slow, and it wasn't really just in time, it was just behind time. If I massively replicate and completely over-provision, it's fast. And with so much computing and storage around, the application is becoming the service rather than just a window. So we're not building functionality into networks, we're stripping networks and using them less, treating them with distrust and avoiding them. A richer network is economically anti-gravity for the world we are building. This is all about application-centric networking. QUIC is an application in user space. It's not a kernel function and it's not a network function. That's where we're heading. And so the network that I think a lot of you cut your teeth on in architecture, I did too, was built like this, where to scale, we did role specialization. Instead of full service networks doing everything for everyone all over the world, we actually created speciality networks that did particular roles. And this almost dates back to the NSF. This is the 1990s internet. Today's internet, well, there's no transit, there's no mid-levels, none of that. The CDN data feeds use private networking to feed their points of presence. And what we're building at the moment is local peering exchanges and CDN service cones. At some point, we're going to get rid of all that nonsense, and the CDN gets its points of presence back in the Access ISP. And if you remember the original Akamai model where they put their servers inside the racks of ISPs, yeah, right. Same thing again. So who needs transit? Who needs transit? Well, users don't send packets to users anymore. They stopped talking to users yonks ago. All content comes from CDNs or you die. There's no universal service obligation. There's no regulatory provision. So who needs transit? Everyone is doing closed transit. Everyone. And that's the entire market for submarine cable systems. It's all about servicing the content distribution problem. And it's not really a problem. It's a problem of abundance, if anything. And then you sort of think, well, what's transit in this world? Because if these CDN caches sit closer and closer and closer to the edge device, then the network is irrelevant as a shared common medium to this activity. All the value is in content. Transit's irrelevant. And so if transit's irrelevant, what's the routing problem? That's really interesting because there is none. If all that data is delivered across just one AS hop, then who needs a full table? I aim default at whatever the local sort of CDN point of presence is, that aggregated beast, and it just sorts it out on service names. So no one needs a full table anymore. And quite frankly, the cost and benefit of transit is almost a replication of all of that QoS engineering of the late 90s, early 2000s, where ISPs found themselves spending a massive amount of money building quality of service and service differentiation at the packet level, but they were getting less than 1% of their revenue from all of that cost, and it was no traffic. And at some point, the answer was, nah, let someone else do it. We're not going to do it anymore. We're just not. And at some point, this whole issue of a global shared routing resource is too expensive to maintain because no one uses it. The cost and benefit don't add up. We just walk away. And so if the internet is today just these discrete CDN service cones, and that's all it is, who cares if you and I share an address? As long as your CDN point of presence near your town addresses you uniquely, you don't care what mine is with respect to my CDN point of presence. We can both be host number one, and nobody cares. And quite frankly, do I even need a global naming system to produce a global address? Do I even need a global routing system? And what's this global network nonsense? It doesn't matter anymore. And I think part of the issue was the paradigm we built. The paradigm we built was a paradigm that doesn't work anymore. We were building a telephone network for computers, a two-way network, which was true peer-to-peer. You didn't speak to the telephone, you spoke to someone else via the telephone. But quite frankly, no one does that. Nobody does that. I'm speaking to a WebEx data center. You're listening via a WebEx data center. They're different data centers unless you live in my town, and nobody cares. What's between those WebEx data centers is none of my business and none of your business. The fact that it works is good enough. And so what you're doing is actually building a content distribution role as an enterprise service framework rather than this shared public carriage service. The telephone paradigm has reached the end of its relevance for the internet. And there's no point trying to re-engineer that. The cost and the benefit don't work anymore. As Tony Lee said in chat, isn't there a long tail of residual use? Only if there is a long tail of ISPs willing to sacrifice large amounts of money on nostalgia. Only if they're still running the horses and carts when everyone else has shifted across to electric cars. And so what we're doing right now is actually privatize all of those internal parts of a shared carriage network, stop sharing, remove it from public regulatory oversight, double benefit. And we're in a completely different world. So it's not just centrality of content and service in routing. No. This shift in the way users use the network, and I'm not even sure it was a user choice other than preferring fast and cheap, but in making a massive system massively fast and massively cheap, we leveraged abundance to actually get rid of the network and produce a whole bunch of exclusive use private distribution systems and only come together in that last mile to actually access the user's device. And so this isn't just the death of transit and the routing of the death of transit. It's actually the entire network as a common shared glue that dies here, because service provisioning is actually inside Amazon, Microsoft, Google, Fastly, etc. It's within cloud providers and distributed data centers. And quite frankly, these edge computers are now basically televisions into that clouded world of data. The distinction between personal and public just disappears. Everything is now corporately owned private. The regulatory role is now irrelevant, which is a sad position to be. And quite frankly, because this is a big money game, the largest, 10 massively public capitalized players on the global share market control everything. And they're so good at their role that the barriers to entry are complete. And we are now not talking a competitive environment. A bit like the Gilded Age in the US in the 1880s and 1890s. What we're really talking about now is how long these folk will be able to preserve their future. And just as a word of warning, JP Morgan is a massive bank, still 120 years later, because it managed to buy not only itself as a preeminent position in finance in the 1890s, it bought 130 years of future because of it. And that's what we're building. That's exactly what we're building. This is a cartel, and it's a cartel that isn't shared, and it's a cartel beyond regulatory oversight. Network-centric functionality, commoditized, irrelevantized, and pushed out. Lower cost, higher speed, and better agility means everything is an application. Why? Because the money is in content, and nobody's willing to make wait for the infrastructure providers to make the investment. They're too slow, they're too dumb, they don't get it. So everything becomes an application. Why is Quick up in user layer rather than the kernel? Everyone got bored with waiting. So you just play with what you can and move far faster than anyone else. Why do we have a common DNS when everyone's waiting for the CPE devices to upgrade their rather crappy versions of DNS resolver libraries? Hey, I can just put the DNS function into the browser. I can just leap across all that crap infrastructure and go to the DNS resolver of my choice over HTTP3. I can use my money to get around the problem. And what's this single DNS universe when I don't care anymore? I'm a browser. I just want names for my function. I don't care about you. So what defines the internet now? We had this idea that we're all working on common protocols, common address pools, common routing systems, common names. We're not. We're not. We've minced those and discarded them. What we're looking at now is this totally disparate collection of services that if they share anything, they just share common referential mechanisms. When I use the word Facebook, actually I should use the word meta, shouldn't I? It's so meta. You know what I'm talking about. And that's all it is anymore, common referential mechanisms. So we didn't deliberately get here, but we are here. And it's not a nice place to be. As Andrew Jackson said in 1830 in the US, monopolies always end up price gouging and entrenching their monopoly. Always. It's a fact of life. And we have exactly that situation. And the real question is not how do we fix it, but is it fixable? Or are we too late? This is the dilemma I think we face ourselves, not just as the IETF, but as everyone here. What we've built is unfixable. It's just too late. With that, I will come down from the clouds, come down from this massive overview about an alternate view about it's not about networks anymore. It's all about applications and content. And it's all happening as an overlay, leveraging abundance, where previously there was a scarcity situation. We're now leveraging abundance as far and as fast as we can. And hand it back to you, Adrian. Thank you.
Thank you, Jeff. That's, well, as always, incredible. And you may have noticed that the chat window has gone totally crazy with people reacting.
Far busier and far faster than I could track while I was speaking.
Well, yeah, I'm amazed that you even picked out any points from that. So we'll open it up for questions to all the speakers and discussion from everybody in the room. But I'm going to get mine in first, probably to you specifically, Jeff. Do you think that the transit is dying as a percentage of the total traffic or absolutely?
The common metric that we told ourselves even 4 years ago after Netflix made some massive incursions into this space, and this is 4 years old, was that streaming of video was 70% of downloads. Now, I'm not an ISP anymore. I used to run one back in Australia in the 90s and 2000s. 70% of the traffic then came into the country from US, Europe, whatever. And so we made our money by basically making sure that the submarine cable investments were, if you will, clever, because that was our cost base. With 70% of all the traffic that these ISPs are selling coming from a local position, then it doesn't matter anymore, right? It just doesn't matter. And the problem is that maintaining this transit business, maintaining this routing system is expensive, but no one's using it. We're not making money from it. And so if I set up an ISP that got you to Facebook, Akamai Cloud, got you to the CDNs and said, no, you want to go somewhere else? That's not me. Go and become an ISP. I would make money. I would make a lot of money. And everyone else would look at me going, but that's not the internet. And I would say, well, that's not what I offered. I offered you content. And I'm not even sure that users would notice the difference. And that's the sad place we're in. And that realization that no one values transit, because this is a deregulated market, not one where there are minimum requirements for universal service, then if no one is willing to pay the cost of it, ultimately it dies, and that's what's going to happen here. I don't know if that was an answer or not, Adrian.
Well, it was something of an answer, and it gave people a chance to go +Q in the chat room or raise their hands. So since I'm looking at the hands first, Andrew, please speak.
Hi, Jeff. Very interesting presentation, and it's particularly curious from my perspective here in Africa, where we're one of the companies that are investing heavily, hundreds of millions every year, building infrastructure, fiber cables, pairs, etc. And we're still seeing a growth in the transit. But from an IETF perspective, I'm quite curious in when we start talking about the network in kind of almost islands like you're referring to, how does this play with what we are seeing, where suddenly everybody is trying to introduce everything into so-called limited domains? You see that term limited domain in RFC after RFC, in draft after draft. And I wonder, in the context of what you're saying, where there is no centralized kind of internet, how you feel about that and what dangers it creates, where we effectively start breaking down standardization by introducing everything as limited domain that, well, may or may not leak and potentially break things. So I'm just curious as to hear perspective on that.
You know, when we got rid of the telephone company as the technology orchestrator, that there were suppliers who built to telephone company standards, and whether it was cable, whether it was a handset, whether it was a switch, almost every aspect of that technology was orchestrated by, you know, the telephone company, who was the service provider, funder, etc. Then it was very clear what was going on here. And the standards bodies was actually an orchestration between various telephone companies in order to get efficient supply channels. We threw that out when we threw out the telephone companies. We became a market. And at the time when we thought this market was going to be viable as a multi-provider competitive market, we needed standards more than ever, because standards were the way that this market, someone could enter with a product and sell to multiple consumers, and whether it was fiber cable, whether it was a piece of software, whatever. And so the IETF was the way in which that market was sustained. But the assumption is that no single player can squat across the entire fabric, can actually do its own cable, do its own software, do its own platforms, do its own platform operating system, do its own, search engine, do its own, browser, do its own. You see where I'm going? That if someone doesn't need to share and doesn't need to orchestrate across multiple providers, their need for standards is actually lower. Now, you're saying in a part of the world in Africa, you don't see that. And you are right, you don't. But what you do see is shopping malls. What you do see is the incursion of orchestration in the retail sector, where the small shop disappears and the large shopping mall franchise moves in. Ultimately, consumers are going to get organized in this environment over time. And once we've finished building out the developed world, and we haven't finished yet, and we've reduced the size and cost of these, CDN points of presence to the point where we can now look at the rest of the world and push the same technology everywhere, then, the end is inevitable. It's just simply a matter of time at this point. And so there are niche opportunities in a vanishing market for transit. But that's all they are. Niche opportunities in a vanishing market. And money can be made. I'm like, you could still breed horses in the 1920s. It just didn't make sense in the 1980s, I guess. And it's the same kind of world that we're doing right now. As abundance makes everything cheaper and more plentiful, our entire supply fabric changes. And the folk who think that there is a role and a place for increasing the functionality of a shared common resource in networking, I think are making a bet that this abundance is limited and it's going to swing the other way. I wouldn't like to make that bet myself. I don't think we've pushed physics to the end yet. And in the same way that Moore's law, despite everything, continues to be prodigious, what we're doing in fiber just continues to be inexplicably prodigious. And as long as that happens, and as long as we're so far ahead of the demand that we can do abundance, then our entire model of networking, which was based on the telephone view of rationed scarcity, just doesn't cut it. And the folk who do abundance become the giants of this world, and the folk who do rationing have disappeared. Gee, that was a long answer, but sorry.
So I wonder if the other two speakers want to chime in there, because it seems to me that their solutions are in some way also limited domain solutions, and are they seeing limited domains as a solution or part of the problem? Gregor or Mikhail?
I don't think so. Because, or I guess, as far as the stuff I'm doing is concerned, like it's changing how the network layer works, but that would be kind of useful in whatever situation it ended up in. I think what that situation actually ends up looking like is probably above my pay grade.
You can always aspire to more pay. Okay, let's go back to questions. In my list, I've got Dino next.
Hi, I have a question for Jeff. Jeff, I'm going to try to build a decentralized use case that I think is useful, that I think the network can support today. And I'd like your opinion to say if you think it's useful. Yes, all our packets go up to Google and Amazon whenever because we care about that content. But let's say you and I live in the same neighborhood. We just had a storm, so we each lost our cable connectivity to the internet. But we want to find out if our families are okay. You have a cell phone, I have a cell phone. Our Wi-Fi access points are up in our house because we have power. Shouldn't I be able to send packets to you directly? We know the network can do that, but we don't have applications because the applications always want to go to some server and hairpin our iMessage or our WhatsApp or whatever. Wouldn't it be useful for me to talk directly to you, me an IP address to you an IP address?
Dino, there are many things that are useful, but what this industry tends to provide are things that make revenue. And part of the issue is users, you and I, have an incredibly warped view of risk. And sometimes we just don't pay to have the, if you will, insurance about risk. 40 million people live in California, an active earthquake zone. Another few million people live beside the Cascade Fault. If we were rational humans, we would have left there years ago because, when it comes, it's going to be horrible and it's not going to be long. And so you're saying, wouldn't it be good if? And I'm saying, yes, it would be good. I agree with you completely. But the corollary is, how do you pay for it? How do users value that service, even if they're only going to use it when the Cascade Fault re-triggers itself? And the common reaction, which I think is also the California reaction, is, nah, it hasn't happened for the last 100 years, ergo, it won't happen to me. And it's kind of, well, that's fallacious logic, but the answer is, that's human logic. Get over it. And so looking at what we can do and what we're paid and what pays to happen are fundamentally different things. And part of the issue we've found is that as we've concentrated money at the application level, and it's all up there as money as content, they've stopped subsidizing the network, and they're sick and tired of waiting for the network folk to reinvest because those network folk are now getting less and less money per byte. And so there is no money. Verizon is a mere shadow of its former things that it bought. And they kept on buying folk to try and get more money because the money was drying up. They don't reinvest. They don't, innovate because it costs money. And so what do the application folk do? Everything is in user space. Everything is tunneled across a dumb network. I can't change the infrastructure anymore because they're not going to pay for it. And I'm damned if I'm going to pay them. And so you don't. And so what you do is everything becomes lifted up into the application area, because that's what each of us control with our own money. The money speaks. It's more agile. I have control. I do an update if I'm Chrome every 2 weeks. I have control. I have agility. I have flexibility, and I express it. And that's where we're heading. It makes me sad because we're not cooperating anymore. We're just enclosing and doing limited domain work. Yes, that's exactly what we're doing. And by the way, in all of this talk, I haven't said good or bad. In fact, personally, I think this is one of the saddest things we ever did to ourselves as mankind. We invented a shared resource of digital computing, which was truly amazing. And now in the process of ripping it apart ourselves. You know, we are the Vandals and the Goths that ripped out the Roman Empire. Well done us. Unconsciously, whatever, but we did it.
All right, let's try to squeeze in one or two more. Turles, you're next.
Thank you very much. You certainly ramped up the Doom level since the last time I heard you speak about that very nicely. So I've heard, a lot of real and or imagined, problems being, spoken about by ISOC and IETF leadership, but I'm not aware that they would have addressed the issues you're talking about in any, comprehensive fashion. So I was wondering what your understanding is about, ISOC and IETF leadership's position about what you're talking about.
I follow the DNS a lot. And it's not just because the DNS fascinates me. It's actually because I think where the role of applications and infrastructure is becoming, that rendezvous between the referential mechanism of where I want to go to and how I can actually be steered to the data center that's closest to me is where this is heading. The SVCB records, the HTTPS records, the arming of the DNS, and the implication of fragmentation. This is not the DNS. It's a referential resolution function that is now becoming appified and segmented and fractured. And it's almost we're walking there without understanding. And I haven't heard leadership in this because I'm not even sure it's a leadership thing. But it's the one place where the DNS, where this battlefront is actually there if you care to look. And it disturbs me that we've gone there almost as, well, it was a contribution, we'll standardize it. Yay. But what really does it mean? And the answer is, well, be very afraid because it's not the DNS you thought you knew. So, yeah, it's difficult to spend the time to unpack some of this work, but I think the DNS is, oh God, don't go to DNS ops. It's already big enough. But that's the place where this tension is absolutely upfront and there, coupled with DNS privacy, et cetera, but that's the point. Thanks.
All right. And I think Jari is going to get the last question.
Yeah, thank you, Jeff. This is very enlightening, as always. But I have to say that your take on privacy and progress there was a little bit too cheerful for my taste. So if the attacker or the danger is on the path, then yes, we made a ton of progress. But if they are at the server or they are a government who has access to server, then we haven't really made much progress at all, perhaps the reverse. But I also wanted to say another thing, maybe a bit more constructive, and that is that you sort of speak about this in terms of sort of a market behavior or market failure, perhaps. But I think this is actually baked in math and physics. Like it was sort of inevitable in some way that you have to put content near users and replicate it massively. And I think the mistake is not perhaps how the market has behaved, that has been predictable, but the fact that we have been maybe working on the wrong things. We've had this idealistic network picture in our heads where perhaps we should have been talking about the, how do we get content to different places around the world and how to standardize that, what should be standardized. And so, and I actually don't think it's necessarily too late yet, because there's lots of applications people who don't particularly like the fact that they're tied to various setups where they have to pay a fairly large sums of money for the cloud and other services around the world and not be able to move around easily and compete. So I think there is some room for fixing this.
It's a tension, isn't it, Jari? Because obviously the incumbents want to resist that because you're actually undermining their future when you start to talk such revolutionary topics. But I think you're correct in saying this is at the application level where the tension is. The rest of the infrastructure has been commoditized, put in its box, and there's no room. And all of this thought about new IP, this thought about arming the network layer with identities and locations and content references is a fine thought academically, but it just doesn't seem to cut where this industry wants to push. And it's pushing at the application level. The rest, we're kind of going, it's a wasted space. There's no money left in it anymore. We're not going to change that. In the IETF, we're so good at solving yesterday's problems, but that's a human thing. It's not an IETF thing. We are really good at solving yesterday's problems. The issue is that the folk who are solving their own problems for tomorrow don't want to share that problem and share the solution, because the rewards for getting there first are literally rewards of the scale of Zuckerberg's billions, rewards of the scale of Elon Musk's billions. And so the entire sharing philosophy of the tech community of the 1970s and 80s has largely disappeared through that process. And that's too what makes me sad. It's only, God, 7 in the morning, and I'm already very depressed. I'm very sorry about that. I hope the rest of you are being a little sunnier. Thanks.
Jeff, it's time to start drinking, clearly. I want to thank all three speakers and wrap up. It's given a lot of people a lot to think about. I did like Dino's comment in the chat, which was, let's stop trying to predict the future, but instead create it. And maybe that's what research is about, if research can actually manage to link itself to economic and commercial reality. I'm going to take 1 minute to just to say that we've been thinking quite a bit about the research in this area, and limited domain came up as a topic quite often, and there were several mentions of semantic routing in the chat as well, and we've been looking at should we be doing something to introduce these concepts into the IRTF and have a discussion from a very routing oriented perspective. So we've put together some stuff that you can see on the slides, objectives and scope, and practically we've dumped those into GitHub so you can have a poke around and talk about them on our mailing list. And the final bullet on this slide says, plan to discuss with Colin as soon as our ideas have crystallized. Well, we actually started talking with Colin last week, a little ahead of the crystallization of our ideas. And the conclusion of that was that, well, maybe this fits in existing research groups, maybe a bit of ICN, maybe quite a lot of COIN, and we should probe around and see whether there's a good home. So we'll be pursuing that, and we would seriously welcome comments and thoughts that people have. And with that, and more or less on time, well, a minute over, thank you all, and good evening, good morning, and yeah, thank you and goodbye.
Thanks for organising this, Adrian. Cheers.
Thank you. Cheers.